Hello to all my dear friends. I hope you guys are doing great. I am Aishwarya Sharma, Civil Wallah, once again welcoming you on the platform Gate Wallah. It's a Gate Wallah English channel and all the content would be delivered in English language only, and I am welcoming you on the last session on RCC. This session is somewhat special. It's not very important from Gate point of view, but WSM basics, it is a type of thing which each and every student must know. If they are studying RCC, then quite basic things about working stress method they must know. So by keeping all those things, I have brought this session for you guys. So let's start our session on working stress method, and all the basics we are going to cover here. Okay. So agendas of this class is to study about the assumptions involved in the working stress method, modular ratio, what is modular ratio that we have to see, and how to analyze beam by using working stress method. So these three topics we are going to see together, but this is not the complete coverage, I am telling you, because by doing this you would be able to match some catch some basics, but study would be confined only till singly reinforced section. It can be extended to doubly reinforced section, design, or you can say apart from the design, flange sections may also be there. Okay, but here we will be keeping only singly reinforced section in mind. Okay, so let's proceed in our section. As I told you that in RCC broadly three design philosophies are used. One is WSM, another two are LSM and ULM, okay, ultimate load method. And one more thing is there, we have studied our entire course based on limit state method, okay, and working stress method, what is the basic difference between LSM and WSM? I also covered the same, I think, in my lecture number 2, but let me tell you one more time that in working stress method we are ensuring the safety of our structure only by underestimating our material, whereas in limit state method we are underestimating our material as well as overestimating our load. So there we are ensuring safety by underestimating our material as well as overestimating our load. Are you getting it or not? Okay. So in working stress method, factor of safety will be involved only in material. So no factor of safety is involved in load. So if you have to design your beam for 100 unit, then you have to consider design load as 100 only. But yes, in stress point of view, from material point of view, what you can do, you can underestimate your material up to a higher extent. Okay. So let me start the session with assumptions involved in the working stress method. So there are total 4 assumptions and 3 more hidden assumptions. So first of all, let me introduce these 4 assumptions which is mentioned in Annexure B, IS code 456-2000 Annexure B. First is plane section before bending will remain plane after bending. This I have explained so many times that a section before bending, okay, if it is plane, if I have considering 3-4 points here, then even after bending as well, these 4 points would be coplanar. Okay, so strain would be there, plane would be changed, rotated, but still all 4 points or considered points will lie on the same plane. Okay, so the outcome of this assumption is this, that strain diagram is linear. Okay, assumption number 2 is also similar to limit state method assumption, that all the tensile stresses are taken up by steel and none by concrete. It means that whatever tension is there, that has to be taken by steel. Okay, so concrete in the tensile zone is to be ignored. Sometimes they can specifically permit some limited amount of tension, that is a different case, but majority of the clauses as per working stress method based on uncracked section. Okay, like pre-stress concrete, water tanks, for them we are using different code, but there they also allow some amount of tensile values. Okay, the next is the stress strain relationship of steel and concrete under working condition is linear. So this is the assumption which is making our life very easy in WSM. Although the same assumption was not holding good in LSM. In LSM, the stress strain curve of concrete was parabolic and then rectangular. So due to that, so many complications occurred. But here the stress strain relationship is linear. So you need not to worry much. Are you getting it or not? Okay. So next is the modular ratio M. It is having a value of 280 upon 3 sigma CBC. Okay, although I am going, after this I am going to take modular ratio only. But what is modular ratio? Modular ratio is like a conversion factor. If you are dealing with a section in which more than one materials are involved, then for making your analysis easy, what you guys can do, you can simply convert one material into another material. Okay, this you can do. So in order to do that conversion, you need some conversion factor. Like if you want to convert one currency into another currency, then you need a conversion factor for a day. Similarly, if you want to convert steel into concrete or vice versa, then there must be some conversion factor. So that conversion factor is going to known here by modular ratio. Okay, so this is assumption number 4. And although the modular ratio is defined as the ratio of Young's moduli of two material, generally the stronger material comes in the numerator and weaker material comes under the denominator. Okay, so in steel and concrete, stronger is steel and weaker is concrete. So it is Young EC or ES over EC, Young's modulus of steel over Young's modulus of concrete. Okay, so in properties of concrete we have seen how to get the value of EC. It is 5000 under root FCK, and Young's modulus of steel remains constant. It is 2 into 10 raised to the power 5 Newton per mm square or MPa. Okay, but we will not be using that value of M here. The reason being, it's again given in the code that this M considered the long-term effects such as creep. So after introducing the effect of creep, not fully but partially, so they have given an empirical relation which says M is 280 upon 3 sigma CBC. M is 280 upon 3 sigma CBC. Okay, so now let me tell you some more assumptions. Like steel will remain free from the initial stresses. So whenever we are going to cast our section, at that point of time, the stresses in the steel would be 0. Concrete and steel are well bonded together. It means there is perfect bond between steel and concrete, or we can say the strain would be same in steel and concrete. Okay, and this you know from the properties of concrete, it's 5000 root FCK. This is 5000 root FCK here. Okay, now modular ratio, as I told you earlier, you can call it conversion factor, or you can call it section transformation tool. You know, working stress method is also known as modular ratio method. It is also known as deterministic approach. Okay, are you getting it or not? And this modular ratio, conversion factor or section transformation tool is simply going to convert one material properties into another. Generally, common sense says if you want to replace a stronger material by weaker material, then the amount of area required of weaker material would be more than that of a stronger material. Similarly, if you want to replace stresses, so in stresses, weaker material would be able to take some fraction of stronger material stresses. So if you want to convert area of stronger to weaker, then in weaker material requirement would be more. So area would be multiplied with what? With modular ratio M. Similarly, if you want to convert the stresses of steel into stresses of concrete, then concrete stresses would be sigma st over M, sigma st or T over M. Okay, so division would be there. So it is known as the section transformation tool. So how it is the section transformation tool, I can explain you quickly. Suppose I do have a column here. Suppose I have a column here, and over this column, let's suppose there are several reinforcement. Let's say these are longitudinal bar. So recently we have completed column. That was our last to last topic. So these are longitudinal bar, and over this bar I have applied some load P. Okay. So after the application of this load P, what happened? So this cross section is going to be shared by two material. One cross section, one material is steel with the orange color. Minimum number of reinforcement in square column is 4, and another material is this, I am saying it is ASC, and this is another material, let me call it AC. Okay. So the total load here would be shared by concrete plus steel. This one thing is sure, total load here will be taken by concrete plus steel. Okay. One thing is common here, after the application of this axial load P, the amount of strain deformation would be same in concrete as well as in steel. Okay. So whatever is the deformation in concrete, same deformation you can see in steel. This is what called bond, this is what called strain compatibility. So if I am going to equate the deflection of both the material, then P, L would be same upon A, E, S would be equal to PC L upon, I hope you are getting it. So what is PS upon AS? PS upon AS is stress developed in steel, is equal to PC upon AC is stress developed in concrete multiplied by ES over EC. This ES over EC is known as the modular ratio. So one thing we can say, it is M times of sigma C. So it was intuitive as well. It was intuitive as well. If you want to convert the stress of steel from concrete, then steel is stronger, you need to multiply, you need to increase the value of stress of concrete, or you can say stress developed in concrete is 1/mth of stress developed in steel. Okay, this was our first conclusion. What is our next conclusion? It was related to area, I guess. So as we know that total P is given by PC plus PS. So what is PC? PC is nothing but sigma C into AC. What is PS? It is sigma S into ASC. This is the total amount of okay, if I want to replace the entire material with concrete, means sigma C into A equivalent, then here you can see it is sigma C into AC. So sigma S we have recently seen, it is M times of sigma C. So after replacing sigma S by M times of sigma C into ASC, so we can see that equivalent area would be how much? Equivalent area would be original area of concrete plus M times of area of steel. So simply, if you want to convert the area of steel into area of concrete, or area of a stronger material into the area of weaker material, then you have to multiply your area with modular ratio. Okay. So this is the second conclusion. Okay. But yes, once again I want to remind you that this value of M, ES over EC, we are not going to take the same in WSM. In WSM, the value of M is empirical after partially considering the effect of creep, and sometimes they say shrinkage as well. Okay, so if we are using 280 upon 3 sigma CBC, then we can apply this rule. Okay, area can be converted and stress can also be converted. Are you getting it or not? Okay. So we are not considering here ES over EC, as in this M is not considering the long term effect like creep. In some books it is also written shrinkage, but code is saying creep only. Okay. Okay. So conclusion is this. So total 2 conclusions are there which we need to draw. Stress in the stronger material like sigma S is M times of sigma C. Area of weak material. Obviously, if you want to replace the stronger thing with the weaker material, then amount of material would be more. Okay, dear? Okay. Now, I am going to show you how to analyze a simple singly reinforced beam by using the concept of working stress method. Okay. So, what we can do here, let me draw a simple beam for you guys, only from detailing point of view. So, this is the length of the beam, Let's suppose this is a support condition. Let me call it simply supported beam. Okay, so the reinforcement would be somewhere here. We generally want to keep our reinforcement in the tension zone. We cannot keep it just at the outer face, as outer face is the most critical, but still we cannot provide our tensile reinforcement there. I hope you know the reason, because if you will be providing the same at the outermost layer, then it would be prone to environmental, just a minute, yes, then it may contact with the atmosphere, moisture, and moisture is the main cause for your corrosion or rusting. Okay, so that is the reason we need to apply some minimum amount of cover. Okay, so if I want to draw a cross section here, then cross section would be like this, cross section would be like this. What is happening here? Cross section is like this, and amount of steel would be somewhere here, like this. This is AST. The effectiveness of the section is lying only till the CG of the tensile reinforcement. Okay, this is effective D, this is overall D, this is overall width. Okay, and this is known as effective cover D dash, or sometimes it is written as DC. Okay, so the requirement of DC we have also seen. Effective cover, nominal cover requirements we have seen depending upon the severity of the situation. It is moderate, mild, severe, very severe, extreme. So we have seen what are the suggested nominal covers as per IS code. Okay, in slab chapter I think I have given you the table. Okay, now dear, catching would be easier for you now, because all the technical stuffs, all the procedure you know. All you need to do is you need to just change that parabolic rectangular portion into the linear one, and other than that, one more thing you have to keep in your mind, that this time no factor for load, only there is a factor for material. Okay, so yes, I will also introduce soon that what all are the partial factor of safety here. I hope you remember the partial factor of safety of concrete and steel in LSM. In LSM, the partial factor of safety for concrete and steel was 1.5 and 1.15. Although in concrete, first of all, we have taken the 67% of the characteristic strength, hence we applied the partial factor of safety of 1.5. Similarly, on steel, we have provided the partial factor of safety of 1.15 because the reliability on steel was more, because quality control was better there. Okay, and in working stress method, the partial factor of safety of concrete is taken as 3. You might be surprising, it is quite high. Okay, and for steel it is taken around 1.7 at 1.8. Okay, so that is a partial factor of safety. And okay, so this is a beam detail. So if we are using, let's suppose M25, so in working stress method we are going to use the term sigma CBC, and this is concrete in bending compression. So it is 25 by 3, so almost we are going to take 8.5. Okay, nearly in MP only. So similarly, if FE415 is used, then for it the factor of safety is 1.8. So we are going to take how much? Like 230, I guess. Okay, in MP only. Okay, isn't it? So here the concrete area would be this much. So there is an entire area of concrete which is going in bending compression, and strain diagram here is going to be linear, stress diagram is also going to be linear. Okay, okay, it's like this. So if stress developed here would be C, and stress in steel is T, then stress developed in the concrete would be T by M, and strain diagram is also linear there. But when it comes to steel, so there is a steel is concentrated at some local portion, local area, so no tension from here to here, because all the tensile stresses would be taken up by steel. So when this stress will be acting on this area, so for steel is like just like stretching in direct tension. So that's why the subscript is ST, stress in steel in tension, or you can say stress in steel in direct tension. Although the procedure is bending, but bending stresses are developed only at some local portion. So that's why we are denoting this value by sigma ST. Okay. Had there been a case of entire steel section, so in that case we could have said that yeah, the stresses in steel would be developed from here to here. So we need to define some new terms like sigma SB, S like that, SBC like that. Okay. So this is a case. Okay. So for analysis we are having 4 steps like we had in case of limit state method: calculation of critical depth of neutral axis, calculation of actual depth of neutral axis, calculation or you can say the comparison between the actual and limiting depth of neutral axis, and calculation of moment of resistance or the maximum safe load which your beam can take safely. Critical depth of neutral axis. First of all, let me come over critical depth of neutral axis. Dear, this is the depth of neutral axis such that the maximum allowable stresses in steel and concrete are going to reach simultaneously. So what are the maximum allowable stresses in concrete? It is sigma CBC, 1/3 of the characteristic value. And what is the maximum allowable stresses in steel? It is sigma ST, after dividing the value of yield strength by 1.8. Okay, so one thing is sure, if this is sigma CBC, this is sigma ST is in steel, but if we have converted this section into a homogeneous one, then it is sigma ST by M. So such a depth of neutral axis will be known as critical depth of neutral axis. I repeat, critical depth of neutral axis is such a depth of neutral axis when the maximum permissible stresses in steel and concrete are going to reach together. Okay. So after solving it, sigma CBC upon XC is equal to sigma ST over M divided by D minus XC. After solving this here, you would be getting the expression of XC. Okay, so what is XC? D over XC minus 1 is equal to sigma CBC divided by sigma ST over M, then add plus 1 here and reciprocal the things. So final expression which you are going to get here is this one. One important thing to note here. What is that? This expression you are getting after keeping the value of M as 280 upon 3 sigma CBC. So sigma CBC and sigma CBC will be cancelled. So 93.33 is nothing but 280 upon 3. So here as well you can see that the critical depth of neutral axis is only depending upon the grade of steel. It is only depending upon the grade of steel. The results were same in LSM as well. There as well you were getting the value of axial limiting, and that was equal to KD, and KD was K. What was K there? That was also depending upon grade of steel only. K was 700 upon 1100 plus 0.87 Fy. So that value of K was depending upon the Young's modulus of steel, which is constant. And on another thing was grade of steel. So here as well you can see that results are depending upon the grade of steel. Okay. So XC value is only going to depend on grade of steel. I hope you are getting it. Okay. So next is actual depth of neutral axis. So like in limit state method, what we did, we simply equated our compressive forces to the tensile forces, and afterward we have calculated the actual depth of neutral axis. So scenario is also same here. If this is C, I don't know what all are the stresses developed at this section, because sigma CBC will be developed at the time of when maximum permissible stresses will be reached. And let's suppose here the stresses developed in steel is T, so in equivalent section it would be T over M. So one thing we can say that if this is XA, then we can say that average force CF is equal to TF if I am going to make, then we can say one thing, that average stress, okay, into area, what is area? B into XA is equal to TF is T by M into AST is the area of steel, but in terms of concrete it is M times of area of steel. So you would be getting CBXA is by 2 equal to T times of AST. Now again, from the concept of similar triangle, I can say that due to the linearity of this graph, I can say C over XA is equal to T by M into D minus XA. So just replace either T or D. Let me write the value of C here. So C is T XA over M D minus XA. So if we are keeping the value of C here, then what you are getting? C is T XA over M times of D minus XA into BXA by 2 equals to T times of AST. So T and T will get cancelled. So from here you can write that BXA square by 2 is equal to M times of AST into D minus XA. So intentionally I have written in this format. What is B into XA? It is the area of compressive zone. What is XA by 2? BXA into XA by 2 is the moment of compressive area about the neutral axis. Similarly, what is M times of AST? It is the net concrete on the tension zone, which is the converted concrete. And what is the lever arm for that about neutral axis? It is D minus XA. So means in working stress method, if you are going to equate the moment of area about the neutral axis, you will be getting the exact value of neutral axis. So whenever we have to calculate actual depth of neutral axis in working stress method, then we can simply equate the moment of area about the neutral axis. So keep this important point in mind. Why this moment of area thing is coming here? Because of the linearity of the graph. Due to this similar triangle, we have replaced our stresses, and due to that this moment area method is coming. Okay, so just by equating the moment of area about the neutral axis, we can get the actual value of neutral axis. After that, again important things come, which is comparison. So based on the value of XA and XC, we can make a comparison between of our section. Okay, so XA value, please don't forget, it is depending upon the geometry of the cross section, it is depending upon the area of steel, it is also depending upon the modular ratio, means it is depending upon the grade of concrete, because modular ratio value is depending only on the grade of concrete, it is 280 upon 3 sigma CBC. So XA value is depending upon everything, every possible thing. It is depending upon geometry, it is depending upon grade of concrete, it is depending upon grade of steel, it is depending upon area of steel. Okay, not grade on steel but area of steel. Okay, so it is depending upon so many factors, whereas the value of critical depth of neutral axis was only depending on grade of steel only. Okay, so now the next step is comparison. So again the three outcomes can be there. Okay, one, when value of XA is less than, is it visible? This is the case here. Okay, I hope now it is visible. So there can be three possibilities. One, XA can be less than XC, another can XA and XC are same, and third, when XA is greater than XC. So if XA is less than XC, so you can see that earlier steel is going to reach its permissible limit first, and concrete is still having some margin. So such a section will be known as under reinforced section. Such a section will be known as under reinforced section. Here developed value of stress in concrete is less than sigma CBC, but yes, developed value of stresses in steel is equal to sigma ST. Another section is known as the balance section, okay, or critical section. So it is known as the balance section. So in balance section, we can see that both steel and concrete are going to reach their permissible limits simultaneously. Okay, and third is over reinforced section. So in over reinforced section, you can see that concrete has reached its permissible limit, but there is still margin in steel. So in under reinforced section, steel is going to reach its permissible limit first. That's why it is under reinforced, means amount of steel is less than some benchmark. In limiting condition, both are going to reach their permissible limit simultaneously, so it's okay. So it is theoretically ideal case. zero wastage case, when both of them are going to reach their permissible stresses simultaneously. And third case is over reinforced section, which was not allowed in limit state method, but here as well it is not preferred much. But yes, you can still increase the moment carrying capacity of a section by giving some over reinforced section. Okay, here you can see that concrete is going to break first, because steel has not reached its permissible limit. Amount of steel is much more here, so it is not going to fail. And due to the more presence of concrete, the amount of concrete is more, amount of concrete is relatively less, so first concrete is going to fail. And nature of concrete is brittle it is brittle, and the failure pattern of over reinforced section comes out to be brittle in nature. So therefore in most of the books they have said that ORS, over reinforced sections, are not preferred. Okay, now after all three cases, now the final conclusion is how to calculate the moment of resistance. So this is C, this is XA, this is T by M. We know that it's going to be XA, we know it's going to be D minus XA. So what is the average force here? It is average stress C by 2 into B into XA. What is the force here? It is T times of AST. How we concluded here? It is T by M into M times of AST. So it is T times of AST. So over this triangular section, this force is acting at a distance of XA by 3 from top. So lever arm would be D minus XA by 3. So if I want to write the moment of resistance here, then this moment of resistance is either compressive force into lever arm or tensile force into lever arm. Either compressive force into lever arm or it is tensile force into lever arm. Either compressive force into lever arm or it is tensile force into lever arm. If section is under reinforced, then you can replace T with sigma ST, but C would be less than sigma CBC. If section is balanced, then replace C as sigma CBC or T as sigma ST, or in place of XC you can keep the value of XC. You know how to calculate XC. XC is 93.33 upon 93.33 plus sigma ST into D. Okay, and if section is over reinforced, then try to calculate the moment of resistance from compression side, because you can keep here sigma CBC, because concrete is going to break first, and T would be less than sigma ST. But still, if you want to find the value of moment of resistance in over reinforced section from tension side, then by using the concept of similar triangle, first of all you need to get the value of T, then you can substitute the corresponding value of T here in order to get the value of moment of resistance. Similarly, in case of under reinforced section, in under reinforced section, if you want to calculate the value of moment of resistance from the compression side, then first of all again you need to apply the similar triangle of in a stress diagram, and from there you have to calculate the developed value of stress in concrete C value. Okay, so all these three possibilities can be there, and theoretically designing and all forces things we are taking benchmark for critical section or balance section, although in practicality we are giving our section slightly on the under reinforced side. Okay, okay dear. So that's all in working stress method. So I hope you can extend this theory in reading W or T section, but it is not required, at least for gate point of view. So that is the reason why I am not taking that part. Okay, I hope you like these lectures, and these would be beneficial for you. Okay, so you can always share your feedback on the comment box, so we will be watching that, and accordingly we will incorporate some corrections. So have a great time ahead. Bye bye, see you soon. Bye guys.